Thank you. I'm happy to be here today to talk about Titan and Dragonfly. With Dragonfly, we are not looking actually for life as we don't know it, or even life as we do know it. What we're looking for is chemistry. And that chemistry that we may find on Titan will hopefully help to fill some of the gaps we were talking about yesterday in that large step between basic chemistry and the development of life here on Earth. So I will talk briefly about what makes Titan special, and then how we're going to explore Titan with Dragonfly, what we hope to learn. And I'll talk a little bit more, in a little bit more detail about the types of chemistry experiments that we're hoping to learn from. So Titan is a moon of Saturn. It's the largest moon of Saturn. It's slightly smaller than Mars, but it is very unique in terms of moons in our solar system in that it has a dense atmosphere. And in fact, that atmosphere is denser than our atmosphere on Earth, so it's actually between Earth and Venus in terms of its atmosphere, even though it's a somewhat smaller body. The surface gravity at Titan is about 1/7 that here at Earth. We'll come back to that. It's out in the outer solar system, so it's cold. It's 94 Kelvin at Titan. On the surface, the bedrock composition is water ice, and the atmospheric composition is mostly nitrogen, like our atmosphere. The next major constituent is a few percent of methane, which does a number of interesting things at Titan that I'll talk about. I mentioned the atmosphere is denser. It's 4 times denser than our atmosphere here, or the surface pressure at Titan is 1.5 times that here on Earth, because it's a dense atmosphere and the time scales, Titan's day and Titan's year, are much longer than ours. It's actually almost isothermal. It's basically 94 Kelvin plus or minus a Kelvin, which means that it's actually a pretty sluggish atmosphere. We don't have the wild temperature swings on Titan that we're used to here on Earth. Like many of the moons in the outer solar system, Titan is an ocean world. It has a deep interior liquid water ocean. So one of the things that methane does in Titan's atmosphere is break down at the top of the atmosphere. And the constituents recombine to form very complex carbon molecules at the top of this atmosphere, up at 1,000 kilometers altitude. And those form aerosols in Titan's atmosphere, which is what makes it a bit hazy if you're looking at it in visible wavelengths. And they fall out onto the surface. But the surface is water ice. And at places where that might have melted in the past, now you have liquid water and complex carbon-rich molecules mixing possibly for extended periods of time. So that's what makes Titan so unique in our solar system. The Cassini-Huygens mission has told us a lot about Titan. We, in fact, have only really known the geology and the geography of Titan for the last 20 years. It's only been in the last couple of decades that we learned what's on Titan's surface. And I'll talk a little bit about this. There are a few impact craters, but Titan, like Earth, has active processes modifying, destroying, erasing impact craters. And so there are actually only a handful of impact craters on the surface. At the poles, there are lakes and seas of liquid methane and ethane. With Dragonfly, I'll skip ahead a bit. With Dragonfly, we will not be going to the lakes and seas. The North Pole is actually going to be in winter darkness at the time when Dragonfly will arrive. So I'll talk more about our exploration region. Those dark regions around the equator turned out to be sand seas. Titan's equatorial region is vast seas of organic sand dunes. We don't actually know how you make organic sand-sized grains, but Titan does, and they are basically wrapping all the way around Titan's equator. There's some hints of cryovolcanism at Titan, of cold volcanism where the lava would be liquid water. And this is one of those examples with a big pit next to a mountain and possibly what could have been a flow field. But there's no evidence of active cryovolcanism from Cassini thermal measurements of Titan's surface. One of the other things that methane does at Titan is that methane plays the role there that water does here on Earth. And so there are methane clouds, what you're seeing here, looking down on the North Polar seas, those dark features, the top of the image, the bright white features are tropospheric methane clouds, and you can see in this movie made by Cassini, the clouds kind of moving a little bit across the surface. This is near the summer solstice, the northern summer solstice on Titan, so the North Pole is illuminated all the time here. And since the end of the Cassini mission, we've been able to use Earth-based telescopes and JWST now to observe clouds and monitor Titan's weather as well. And Titan has channels. And I mentioned the lakes and the seas at the North Pole. It is a surprisingly Earth-like world. If we were standing on the surface, it would be very familiar from a geological perspective, even though the materials are completely different than the materials here on Earth. Nonetheless, the geology and the landscape would look very familiar. The Huygens probe descended down through Titan's atmosphere near the equator. And this is the image it sent back. This, of course, is our moon, but just to give a sense of scale of the features we're seeing here on the surface in this view from Huygens of this gravelly plain with water ice cobbles that look like they've been rounded in a stream, just like here on Earth. So Dragonfly is a mission in the New Frontiers program at NASA. It's the fourth mission in this program. It's the same program with New Horizons that's explored Pluto, and Juno that's at Jupiter, and OSIRIS-REx that brought back the sample from Bennu. We were selected in 2019. We are through our preliminary design phase and our NASA mission confirmation. And in fact, just 2 weeks ago, we successfully completed our critical design review. So that's an excellent milestone. The design you see on the far left is the CAD model from our critical design review. And one of the other aspects of Dragonfly, of course, is mobility, as I'll talk about. And so we've been doing a lot of testing there, and in various wind tunnels and a chamber that APL built that actually replicates the environment on Titan here on Earth, the thermal environment. So Dragonfly is a rotorcraft lander. It's about the size of one of the Mars rovers, of Curiosity or Perseverance, so about the size of a small car. It would fit on the stage barely. It's a large vehicle, which is possible because Titan actually does a lot of the work for us. With the low gravity and the denser atmosphere, it's actually physically easier by a factor of about 40 to fly on Titan than it is here on Earth. And so Dragonfly, like the Mars rovers, will transport our entire payload from place to place to be able to make measurements on the surface, but instead of driving, we'll fly. Unfortunately, at Titan, we don't have a fleet of relay satellites the way we do at Mars, so we'll do direct-to-Earth communication from the surface of Titan. And like the Mars rovers, we're powered by a multi-mission radioisotope thermoelectric generator, which not only provides the power for the mission, but also the heat to keep the interior of the lander warm and at an operating temperature, even though the exterior will be at 94 Kelvin. Yeah. So with Dragonfly, we're fundamentally looking for answers to questions about chemistry. What are the chemical components available on the surface, and what chemical pathways exist that could lead to interesting chemistry? We know that all the ingredients are there and have been there on the surface, and what we want to do is pick up basically the results of the chemistry experiments that Titan's been doing for us. And we want to put that into the context of understanding the habitability of this world in the outer solar system. We want to understand the atmosphere, the methane cycle, the processes that mix, modify, and transport organic material on the surface, and the opportunities for that organic material to mix with liquid reservoirs of water, especially in the past at the surface, at the sites possibly of cryovolcanism, cryovolcanism, but definitely at the sites of impact cratering, where the energy from the impact will have generated impact melt that could persist for thousands or tens of thousands of years. At Titan, 94 Kelvin, we do not expect to find life. Life as we know it certainly is not comfortable at 94 Kelvin. And as we heard yesterday, methane may not be a very conducive solvent for chemistry, for biochemistry, or for prebiotic chemistry to develop toward biology. Nonetheless, we have the capability to identify a number of different chemical biosignatures in case Titan surprises us, in case Titan knows more than we do about that process that takes us from chemistry to biology. We have a suite of instruments on Dragonfly. There's, to understand the chemistry in particular, we have a mass spectrometer, and this is fed by a drill. So we break up the surface material. We can use pneumatic transport. So we got this great cold atmosphere to bring the material into the mass spectrometer and measure the detailed chemical composition. I'll talk a little bit more about that. We also have a gamma ray and neutron spectrometer that will give us information about the bulk elemental composition beneath the lander. And then we have a suite of instruments to measure other aspects of Titan. One of the things that I like best about it is that we can put these detailed chemical measurements into the context of Titan as a system and make measurements about its geophysics and meteorology, as well as understanding the geology of the region that we're exploring with a suite of cameras. And the Dragman instrument, the geophysics suite, also includes a seismometer to listen for Titan quakes, which will be fascinating. So we're going to explore this region on Titan, just north of the equator, around this impact crater called Selk, which is 80 kilometers in diameter. We'll land in between the dunes on Titan. These are longitudinal dunes. It's a very specific kind of dune that is very long-lived. It's actually, there are a few examples here on Earth. Most importantly, in the Namib Desert, there's a suite of, or field of longitudinal dunes there. You can see here on Earth the different materials. Now, of course, on Earth, these are both silicates. The dunes and the interdunes have different materials. But on Titan, the dunes that you're seeing in that synthetic aperture radar image at the top, the dunes have an organic composition, possibly widely sourced from around Titan. The interdunes have a water ice composition consistent with perhaps the primordial crust of Titan. And so by landing in the dunes, we get access to two very different types of materials with different geologic histories in very close proximity. Dunes are spaced just a few kilometers apart. Another reason to land here, again from the Namib Desert, is that those interdunes are perfect landing sites. If you're an engineer designing a lander to land for the first time and fly from place to place on Titan, having a beautiful flat interdune is ideal for a landing site to target. So our approximate landing ellipse is down here, south of the impact crater, and then over the course of our mission, which is about a little over 3 years, we'll traverse through the dunes and interdunes and into deposits associated with the impact crater, where we have the opportunity to measure materials that may be the result of these chemistry experiments, where organic material has been able to mix, perhaps for an extended period of time, with liquid water. I should say this is very exaggerated. Titan's mountains are only a kilometer or so high. The topography is exaggerated here, but like most icy satellites, it's actually pretty low-lying topography. And over the course of the mission, we'll explore a few dozen unique sites. The gamma ray and neutron spectrometer allows us to classify the material on the surface by measuring the bulk elementals composition, as I said, detect minor inorganic elements, salts, which are, of course, important, and potentially reveal near-surface stratigraphy if there's a mantle of organic material, of the aerosols that fall out of the atmosphere, over, for example, a water ice substrate, we'll be able to detect a few tens of centimeters down beneath the lander. And then the mass spectrometer has both laser desorption and gas chromatography mode to be able to measure different aspects of the composition of the materials on the surface, the solid materials on the surface. We actually, at this point, have a better understanding of what the liquids are on Titan, the composition of the lakes and seas, than we do of the solid surface materials, because it's so hard to do spectroscopy through an atmosphere that has methane in it and of course Titan's haze. So what we want to understand at Titan is the chemistry. We have the opportunity there to study the kinds of chemistry we can't study in the laboratory easily here on Earth because the timescales are so long. But Titan has had time to do these experiments. And so we're able to investigate elemental availability, especially the key elements that we know to be necessary for chemistry that would develop toward biology. We want to understand if Titan is producing biologically relevant compounds, amino acids, sugars, lipids, and we want to understand the energy producing pathways. We know there's sunlight, there's less sunlight at Titan. It's about kind of like the full moon here on Earth. But there's also local heating in the case of impact craters, or as I mentioned, possibly cryovolcanism. And there may have been transient habitable environments at Titan. Our focus is on abiotic processes, but we do have the capability to distinguish biological signatures, and a number of them, because you wouldn't want to have to rely on a single potential biosignature if you did detect something. And so we have the ability to, with the mass spectrometer, to look at the structure of the elements, of the molecules, to see if there is an enantiomeric abundance of one or the other chirality. We can look for the patterns in molecular masses and the distribution of those, as well as with our atmospheric sensor, we have the our atmospheric suite, we have a hydrogen sensor to be able to look for evidence of metabolic processes if something like that is happening. But as we talked about yesterday, the focus is on understanding how abiotic processes are working on Titan, and understanding what the abiotic baseline is. On Earth, it's hard to see that because there's biology overprinting it everywhere. But on Titan, that's going to be the primary, we think that's going to be the primary function. And so we have a number of different lines of evidence to be able to follow and distinguish between abiotic processes and water-based biotic processes, or even hydrocarbon-based prebiotic processes. Now, as we heard yesterday, methane may not actually be conducive for that, but what we wanted to be able to do is to see if we would be able to distinguish between processes if Titan surprises us, and it certainly wouldn't be the first time a place in the solar system surprised us. So I've focused on Dragonfly here in the interest of time. We are very fortunate in our solar system to have a wide variety of types of destinations that can each teach us different things about aspects, ultimately, of ourselves. And in the outer solar system, we have this suite of moons. You really couldn't ask for a better suite of moons, a variety of moons, if you wanted to. We have, Titan with its atmosphere and all of its complex chemistry, but its very deep interior ocean. And in Europa, where the Europa Clipper mission is on its way, having launched in October, we have a shallower ocean, less complex carbon chemistry, but a shallower ocean, and the possibility of exchange through that ice shell and the habitability of these different worlds can teach us so much about the different variables and the importance of those variables in the development of ocean worlds and the habitable zone around stars. We're looking forward to both of these missions and what we will learn from each of them and synthesizing that to understand more about our solar system and possibly our own origins. I wanted to thank, of course, the Dragonfly team. This is a picture taken at our CBR just a week or so ago. There's a very large team of people responsible for the work that I've presented today regarding Dragonfly. And I also wanted to thank the organizers of the workshop. The cross-cutting dialogue that we're able to have here with such a wide variety of disciplines and expertise represented is excellent and has been a lot of fun. So thank you.